Hello! In this video I'm going to go over section 2.3, which is about techniques for computing limits. Now if you remember in the last section we looked at two different ways to find limits. We saw that we could find limits by creating a table, and we could also find limits by looking at the graph of the function. And then I mentioned that there's also another way to find limits that we're going to start using called direct substitution. And that's really what this section is about. Let's say you have a linear function, and you want to find the limit of it as x approaches a. So by theorem 2.2, the limit of f of x as x approaches a is simply f evaluated at a, so long as f of x is a linear function. Now remember, linear functions are functions that can be written in the form of mx plus b. M is the slope and b is the y-intercept. So as long as you have a linear function, it's very easy to evaluate the limit as x approaches a. You just directly substitute a into the function. You evaluate the function at a. And that's why this is called direct substitution. We didn't have to use a table or a graph to evaluate this limit. We know that if it's a linear function, we can actually just use direct substitution to evaluate this limit. Okay, so an example of this would be like in this example here. You can see f of x is a linear function. Okay, and because it's a linear function, I can evaluate this limit as x approaches 3 by simply evaluating the function at 3 and finding f of 3. And if you plug 3 into this function, you get 3 halves minus 7, which is minus 11 halves. Okay, and then part B, you can also evaluate this function, g of x is equal to 6, the same way, because g of x equals 6 is a horizontal line, so it's a linear function. It has a slope of 0. Okay, and so if you want the limit of g of x as x approaches 2, you just substitute a 2 directly into the function. Right? Evaluate the function at 2. G of 2 is 6. Okay, so that means the limit as x approaches 2 of g of x is 6. Okay, so that's really nice. Okay, if you have a linear function and you want to find the limit of it, you can actually just use direct substitution to find the limit. Great. Okay, now let's look at some limit laws. We have like 7 different laws here for limits that are very useful. Now, and this is theorem 2.3. Now in this theorem, notice that we're assuming that the limit of f and the limit of g exist, so they're numbers. C is a real number, and n is an integer that happens to be positive. Okay, so the first rule says that the limit of f plus g is the same as the limit of f plus the limit of g. The second one says the limit of f minus g is the same as the limit of f minus the limit of g. Okay, the third one says the limit of a constant times a function. So c is a real number, right? So it's some constant number. Okay, so if you're finding the limit of c times f of x, that's the same as finding the limit of f of x and then multiplying it by c, the constant. Okay, the fourth rule says the limit of f times g is the same as the limit of f times the limit of g. Okay, the fifth rule says the limit of f divided by g is the same as the limit of f divided by the limit of g, provided that the limit of g is not 0. Because if that were true, if the limit of g were 0, then this would be undefined, because you can't divide by 0 and get a real number. Okay, the sixth rule says the limit of f raised to the n power, and remember n is some positive integer. It says the limit of f raised to the n power is the same as the limit of f raised to the n power. Okay, and then the seventh rule says the limit of f raised to the 1 over n power is the same as the limit of f then raised to the 1 over n power. Now there is a little proviso here, provided that f of x is greater than 0 for x near a if n happens to be an even number. Now the reason that's the case is because let's say n was equal to 2, which is an even number. Then f of x is being raised to the 1/2 power. Well, f of x raised to the 1/2 power is really the same as the square root of x. The problem with the square root of f of x. The problem with the square root of f of x is f of x needs to be positive for that square root to exist. If you're taking the square root of a negative number, then that's not a real number. So that's why f of x needs to be positive if n happens to be an even power, or an even number, if n is even. And it's only has to be true for x values near a because we know x is getting closer to a. Okay, so there's a little proviso to Rule 7, and it's just making sure that you're not taking the square root or the fourth root or the sixth root of negative values. Okay, so let's look at a couple examples where we might use these rules just to practice them. Okay, so in this example, we know the limit of f is 4 as x approaches 2. We know the limit of g is 5 as x approaches 2. And we know the limit of h is 8 as x approaches 2. So we're given that information. Somehow we know that. Okay, but what we want to find is the limit of f minus g divided by h as x approaches 2. Okay, well, the way we're going to figure this out is by applying our limit laws. You can rewrite this limit as the limit of the top part divided by the limit of the bottom part. And then the limit of this top part is the same as the limit of f minus the limit of g. And now we know each of these limits. We were told each of these limits, right? So let's go back. The limit of f was 4, the limit of g is 5, and the limit of h is 8. So you just plug in, this one's 4 minus 5 divided by 8, which is negative 1/8. Okay, so using our rules for limits, our limit rules, we're able to evaluate this limit. Okay, what about b? b, we want this limit, but of course we can break this up across addition. So we can take the limit of the first piece plus the limit of h. And then this piece can be broken up itself. The 6 is a constant, so that can come outside the limit. And then you're left with the limit of f times g, which is simply the limit of f times the limit of g. And then, of course, all that gets multiplied by the 6, plus the limit of h. And then once you have it at this point, you can actually plug in each of these limits, right? This one's 4, this one was 5, and this one's 8. And so you just end up with 6 times 4 times 5 plus 8, which happens to be 128. Okay? So using the limit rules, again, we were able to find the limit. Okay, and now part C, we want the limit of g of x raised to the third power. But we know the limit of g of x raised to the third power is the same as the limit of g of x raised to the third power. And we know the limit of g of x is 5 because they told us that, so it's 5 cubed, which happens to be 125. Okay, so those limit rules are very useful. Okay, so you need to get familiar with these seven limit laws. Okay, now let's talk about finding the limits of polynomials and rational functions. So theorem 2.4 says that P and Q are polynomials and A is a constant. Okay, so the limit of P of x as x approaches A is simply P evaluated at A. Okay, so in other words, if you're trying to find the limit of a polynomial as x approaches A, you can actually directly substitute A into the polynomial to find that limit. So again, here's another case where direct substitution works when evaluating a limit. It's also true for rational functions. So if you have a polynomial divided by a polynomial, and you're trying to find the limit of it as x approaches a, by the way, this is called a rational function when you have a polynomial divided by another one, you can evaluate that limit using direct substitution. It's p evaluated at a divided by q evaluated at a, provided that q of a is not 0, because again, you can't divide by 0 here. So we have three cases where you can use direct substitution to evaluate a limit. If you're finding the limit of a rational function, you can use direct substitution. If you're finding the limit of a polynomial function, you can use direct substitution. And if you're evaluating the limit of a linear function, you can use direct substitution. By the way, linear functions are polynomials, so we really don't even need this extra theorem 2.2. That's actually contained in theorem 2.3 or 2.4, because linear functions are polynomials. They're first degree polynomials. Okay? So we have several cases where we can use direct substitution to evaluate limits. Okay, so as an example, suppose you wanted to find the limit of this function here as x approaches 2. Well, this happens to be a rational function, right? It's a polynomial divided by a polynomial. And so by theorem 2.4, we can evaluate this limit by direct substitution. Okay, so you just got to plug 2 into this. And when you plug 2 into here, right, you got to plug 2 in for each of these x's, which they've done over here. If you calculate that, it turns out to be a 1. Okay, so that's the limit of this function is 1 as x approaches 2. Okay, so that leads us to what happens, how do we evaluate limits when we don't have a polynomial or a rational function? Which, in general, we're going to call this an algebraic function, right? What happens when we're trying to find the limit of an algebraic function? Okay, well, we can't appeal to theorem 2.4, okay, in those cases. Let's say you're trying to find this limit of this function right here. This is not a rational function. And it's not a rational function because this top piece is not a polynomial. And that's because of this square root. Okay, so how do we handle these cases, right, where we have just what we would call an algebraic function? Well, you're going to have to appeal to your limit rules, your limit laws. Okay, so let's see if we can't figure out this limit using our limit laws. First of all, we know we can break this up across division. So it's the limit of the top divided by the limit of the bottom. And then we can break this top one up across this addition sign. So it's the limit of the first part, this little square root part, plus the limit of this second part, 3x minus 1. And then think of this square root. That's the same as raising this to the 1/2 power. Those are the same thing. Okay, so the limit of 2x cubed plus 9 raised to the 1/2 power by the root rule that we talked about before, that's the same as the limit of 2x cubed plus 9 first, then raised to the 1/2 power, which is really just the square root of this limit, because raising it to the 1/2 power is taking the square root of it. Okay, so that's where they're getting this first piece. And then the limit divided by the limit of the bottom. And then once we get it to this point, we can evaluate this limit right here using substitution now, because 2x cubed plus 9 is a polynomial. So I know what this limit is. I can find it by direct substitution. Just plug a 2 in, and that's what they did. Okay, so it's 2 cubed times 2 plus 9, and then you take the square root of that. Okay, and of course, let's see, what is that? 2 cubed is 8. times 2 is 16. 16 plus 9 is 25. So you get the square root of 25 for this piece. Okay, now the limit of this piece, that's also a polynomial. It's a first degree polynomial, or you can think of it as a linear function. Either way, you can use direct substitution to find the limit. So just plug a 2 in, and you get 6 minus 1, which is 5. And so this top part is just the square root of 25 plus 5, which is 10. And now we just need the limit of the bottom piece, which again, we can use substitution for, since it's a linear function or a first degree polynomial, however you want to think of it. You plug 2 in and you get 8 plus 1, which is 9. So this actually is 10 over 9. Okay, so that's how we handle the limit of algebraic functions. We just use the limit laws to break it down to a point where we can actually use substitution to evaluate the limit. Okay, so I'm going to leave it here. This is going to be part 1 of this section. And in another video, I'm going to go ahead and talk about the rest of the section, part 2 of it. Okay, so until then, thank you for watching. Bye-bye.